Hi, let's try this again. And I won't make the video as long, I promise. Okay, today we're going to talk about exponential growth and decay and separable differential equations. So let's just start with an example because I think it's easier to see while it's being done. Solve for y if dy dx equals xy squared and y equals 1 when x equals 1. Okay, the first thing we're going to do is try to get these variables separated. So in order to do that, I'm going to bring in that exponent. Next, I'm going to move all of the y's to the left and all of the x's to the right. So that's going to be 1 over y squared dy equals x squared dx. And now from this, I can integrate both sides. Oh, that's not what I wanted. Okay. 1 over y squared, of course, is y to the negative 2. So to integrate that, I'm going to get y to the negative 1, but negative equals 1/3 x to the third plus c. Now what we're going to do is we're going to plug in this coordinate of 1, 1 in order to find c. So negative 1 to the negative 1 equals 1/3 times 1 cubed plus c. This is still negative 1. This is 1/3. And so c equals negative 4/3. Now that we know what c is, we can take that and we can plug that in back up here. So we have, let's see, we have negative 1 over y equals 1/3 x to the third minus 4/3. Okay, so that's coming from this line right here, except for that I wrote this as negative 1 over y, and I put the c value in as negative 4/3. Okay, the next thing I have to do, my goal here really is to solve for y, because that's what I'm trying to do when I solve a differential equation. I'm trying to get back to what the original was. So the next thing I'm going to do is I'm actually going to multiply by 3, because that's going to get rid of the 3's that are on the right side of the equation. Okay, however, I still have y on the bottom, which is no good, so I'm going to do a little cross multiplying and switch these guys, making it negative 3 over x cubed minus 4 equals y. And this, of course, is a perfectly fine answer, but I do want to point out for the AP exam that when there's a negative on top like this, they tend to bring the negative to the bottom and then switch the order. Okay, just for your multiple choice purposes. Okay, a very important thing to note right here. So this is the solution to the differential equation, but this solution is only valid for the continuous section that includes the point 1, 1. Okay, so what do I mean by this? Okay, this function, is it a function? Yeah, this function is not defined where the bottom is 0, because nothing is defined when the bottom is 0. So at the third root of 4, the bottom would be 0. There must be some kind of asymptote here. So I don't know what's happening on the left and the right, but I do know that there's an asymptote there. So what you have to note is that this solution is only valid for this section of graph that has 1, 1 on it, and not the other section of the graph that doesn't have 1, 1 on it. Okay. I don't know if that's going to come up later, but oh well. Okay. So let's see what's next. Law of exponential change. The differential equation that describes exponential growth is dy dt equals ky. Now, I know you might be looking at this and going, there's no exponents here, lady, this is crazy. But exponential growth, so something grows in such a way that its rate is proportional to the amount that you started with. That's really what exponential growth is. We're just describing it in terms of the rate as opposed to the quantity. So K. K is the constant of exponential growth or decay. If K is positive, it's growth. If K is negative, it's decay. Okay, solve by separation of variables. We're going to take this differential equation. This is the standard differential equation of exponential growth or decay, and we're going to solve this. Okay, so the first thing we're going to do is we're going to have to separate the variables. So we're going to have to get this y on to the left, and we're going to have to get t, which is like the x, over to the right. So that's going to be 1 over y dy equals k dt. Now, I know there's no t over here, but that's because the t, it's not in the rate. So now it's time to integrate. K is the constant, though. So the integral of 1 over y is ln y, and the integral of k with respect to t is kt plus c. Just for a moment, pretend that k is like 5. If we're integrating 5, we would get 5x, because the derivative of 5x is 5. So likewise, this is the same thing. It's just with an unknown constant. Okay, the problem here is that we have to get y by itself. Y is not by itself. It's stuck in this log function. So remember that the base of ln is e. So I can get y out of the ln function if I change it to an exponential function. Okay, now I want you to think about this for just a moment. So remember, when you are adding exponents, if you're adding in an exponent, right, we would get x to the 8th. But what that really comes from is x to the 5th times x to the 3. If we were to simplify this, we would, of course, get x to the 8th because we would add the exponents. So over here, that's really what we have going on. So we're going to separate, we're going to separate this into e to the kt times e to the c. And if that's difficult for you to understand, just go back and watch the part where I just did the x and the 5 and the 3. Okay. Constants usually go in front, so I'm just going to switch this to e to the c times e to the kt equals absolute value of y. Y is still stuck in those absolute value bars, but I can get rid of that if I use a plus or minus on the opposite side. And there I have one form of an exponential equation. This, though, is just some constant. It doesn't really matter what it is, and oftentimes it's called a. But what a represents is the amount of whatever you're talking about, when t is 0. So we're actually going to refer to A as y sub 0, the initial y value. And so here's our exponential equation. So hopefully this looks familiar because it is something you should have learned at some point. But this is the equation for the law of exponential change. So we can use that general form of the equation of an exponential for, well, anytime we're dealing with something with exponential change. Okay. The first thing most people think about when they talk about exponential change is compound interest. Okay. Compound interest that's compounded periodically is represented by this formula. P times 1 plus r over n to the nt. I hope someone has taught you that at some point. P is the principal or the initial amount. So for us, it's like y0, but we'll just leave it P for now. T is time. It's usually in years. It doesn't actually matter as long as you're consistent in your units. R is the rate. This is interest, so it's the interest rate. Don't forget, though, you have to change it into a decimal from its percentage. It's usually written as a percentage. And N is the number of times per year. That's not legible. Oh boy. The interest is compounded. Okay. The differential equation that represents compound interest is dA over dt equals RA. And the initial condition is that A of 0 equals P. So the initial amount. Okay. For interest is compounding continuously, the formula is PE to the RT. Again, I hope somebody explained this to you at some point, but basically what happens is when you look at the compound interest equation, when you increase n larger and larger and larger and larger, so you put in some ridiculous number for n like 4 million, and then you calculate this value, you just really wind up with, this. You can get rid of the n, you put the e in, you move the r to the exponent, and it just magically all works out. This is Euler, by the way, and that's why it's named E, because Euler begins with an E. So let's see here. Let's just practice some compound interest problems. Suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have 8 years later if the interest is A, compounded continuously, or B, compounded quarterly? Okay, so let's figure out what's going on here. This is P. This is R, but you need to make it a decimal. And this is T. And if we want to find out being compounded continuously, we're going to have A equals 800 E to the 0.063 times 8. That's not hard. And there's no calculus there at all. And we get this much, 1324.26. If it's compounded quarterly, I have to use the longer formula, which is the 1 plus r over n to the nt formula. R is 0.063. N is, quarterly is 4 times per year. So that's my n. So you see, you earn more money if your interest is compounded continuously versus quarterly. Okay. Now we're going to talk about radioactivity. Radioactive elements decay over time. They decay exponentially, and they're described by their half-life. Now, if you're in AP Chem, you probably deal with this all the time, but half-life is the time required for an element to decay to half its original amount. So if today I have 100 grams of thorium, and in 200 years I only have 50 grams of thorium, then the half-life of thorium would be 200 years, because that's how long it took for me to start with all of it and only wind up with half of it. Okay. The half-life is only somewhat helpful because we really need to know what that exponent is in the equation, the K. Okay, so, but we're going to find that right here. Find the half-life of samarium-151, whose differential equation is dy dt equals negative 0.0077y, and t is in years. Okay, so in order to find the half-life, we're going to have to solve this differential equation. So we're going to have to separate the variables. So y is going to have to move over to the left, and dt is going to have to move over to the right. So we have 1 over y dy equals negative 0.0077 dt. And then we'll integrate both sides. And we get ln y equals negative 0.0077t plus c. Now the solving of this is just like we solved in the very beginning. So e to the negative 0.0077t plus c equals y. Y is an amount, so we're not going to have to worry about absolute value because we're not going to have negative quantities of something. We're going to split this up into e to the c times e to the negative 0.0077t equals y. And remember, we call this guy y0. Just a different name for the same constant. So here's our equation. So I want you to notice that all that really happened here is that this number here, k, just came up as the exponent. That's all that happened. Okay, now what about the half-life? Okay, so the half-life is the time required for an element to lose half of its self, really. Okay, so what I like to do here is I like to just pick an amount, because the actual amount doesn't matter. It just matters that after a certain amount of time, you have half of it. So let's just say we start with 100 grams of this samarium-151. Well, in some amount of time, I want to know how long until I only have half of it, or 50. And of course, in order to solve this, the first thing you would do is divide by 100, and you get a half. So you could skip this whole 150 business, but I remember in college that helping me a lot. So now I have to solve for t, and that's in the exponent, which means I'm going to want a log equation. So I'm going to ln both sides, and I'll get negative 0.0077t, really times ln e, but that's 1, equals ln 1/2. So then divide both sides, and I'll get ln 1/2 over negative 0.0077. And if I type that in a calculator, I'm going to get 90. So we just calculated the half-life of samarium-151. So let's notice here what's going on. Let's have a little summary. So if dy dt equals ky, then the half-life will be ln 1/2 over k. That's it. So let's write that down. If dy dt equals ky, then half-life will be ln1/2 over k. End of story. That's it. Isn't that nice? So you can skip having to do all this in the meantime. Okay, let's have a different example here. At the beginning of the summer, the population of a hive of bald-faced hornets, is growing at a rate proportional to the population. So see this? This is your clue that this is exponential growth. Okay. From a population of 10 on May 1st, the number of hornets grows to 50 within 30 days. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? So from the green highlighting here, that's our cue that this is growth and it's exponential growth because the rate is proportional. Those are the key words there. And I basically got 3 points. On May 1st, we're going to call that 0. There were 10 hornets. In 30 days, there were 50. And then the question is, at what time will there be 100? And they tell us that it's exponential growth. Okay, so what's the form for exponential growth? Y equals y0 times e to the kt. Okay, imagine you were just writing the equation of a line. You would use y minus y1 equals m times x minus x1, right? And you would find the slope, you would put it in, you'd put in the numbers, blah, 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 you'd get your little line. This is really the same thing. It's just a different equation because it's exponential. Okay, so let's put in the information that we know with these 2 points. Just like you would use these 2 points if you were writing the equation of a line to find the slope. It's really not any different. So 50 equals 10. 10 is the initial amount, right? Because t is 0 and y is 10. Equals e to the k. Well, how long did it take to get to 50? 30. And we're going to solve this for k. K is like our m if this was a line. K is like our slope. It's the constant that's specific to this particular problem of hornets. Okay, so we're going to divide by 10 and get 5 equals e to the 30k. The variable's in my exponent, so I'm going to have to take the natural log of both sides. And then k is going to equal ln5 divided by 30. Now, I don't know what that number is. I don't really care at this point, and I'm sure it's disgusting, so I'm just going to leave it alone. So let's go back and write our equation. Right, we have y equals y0 e to the kt. So now I have to fill people in. Y0 is still 10 because that really was my initial amount. And then I have e to the kt, but I now know what k is. It's ln5 over 30. Now I have all I need to plug in any numbers I want. And what they want me to plug in is 100 for y, because we want to know t when y is 100. So we're going to plug in 100 for y, and then we'll have to solve for t. So I'll divide both sides by 10. Again, my exponent is where the variable is, so I'm going to have to ln to get this out. So I have ln 10 equals, the exponent comes down in front, so that's ln5 over 30 times t times ln e, but ln e is 1. So in order to get t by itself, I would times by 30 and divide by ln5. I type that in a calculator, and I get 4292. So what does that mean? That means in about 43 days, there will be about 100 hornets. Actually, I lied. in about 43 days, there will be 100 hornets. Okay, I think we'll stop there, and I'll get back to the next question with tomorrow's video.